Welcome, students. In this video, we are going to study the continuity of trigonometric, exponential, and inverse functions. So let's start. Recall that curves of sine and cosine of x are continuous, meaning that sine of x and cosine of x, these are two continuous functions. Using these two facts, we can show that all other trigonometric functions are continuous. For instance, if we'd like to show that tan of x is continuous, then we can express that as a ratio of sine of x over cosine of x. And sine of x is continuous everywhere, cosine of x is continuous everywhere, meaning that tan of x is continuous everywhere except zeros of its denominator. In other words, tan of x is continuous at all points of its natural domain. All right, so we have the following theorem. If C is any number in the natural domain of the stated trigonometric function, then all these trigonometric functions are continuous. Next theorem is for continuity of inverse of a function. If f is one-to-one function that is continuous at each point of its domain, then f inverse is continuous at each point of its domain. And that is, f inverse is continuous at each point in the range of f. Let's recall that range of f is going to be obviously natural domain of f inverse. All right, we need this statement that f is one-to-one function to show that f is inverse. Recall that if f is one-to-one, then it has inverse. Let's take a look at the following graph. Let's say we have here in black function f that is continuous, and let's assume that it is one-to-one, meaning that one value of x corresponds to a single value of y. And let's recall, to find an inverse of that function, we need to draw a line y is equal to x. And then we need to find a reflection of black curve here about this red line. So we need to find the mirror image about this red line. Then this blue curve is a curve for f inverse. And we can see that if the curve in black is continuous, then the blue curve is obviously continuous too. All right, we can use that theorem to show that inverse trigonometric functions are continuous at all points of its domain. So for instance, tangent of x, arctan of x, is continuous everywhere, is continuous in the range of tan of x, in range of tan of x, and recall that range of tan of x is from minus infinity to plus infinity, meaning that inverse of tan is continuous everywhere. And you can use this theorem to show that all other inverse trigonometric functions are continuous in their natural domains. All right, next theorem. Let's assume that b is positive and not equal to 1. Then function b to the power of x is continuous from minus infinity to plus infinity. And since log base b of x is an inverse of b to the power of x, it is going to be continuous in its domain. And the domain of log base b of x is from 0 to plus infinity. Let's find the intervals where this function here is continuous. In numerator, arctan of x, we said that arctan of x is continuous from minus infinity to plus infinity. ln of x, natural domain, it is also continuous in its natural domain, and natural domain of ln of x is from 0 to plus infinity. And we have a couple of zeros in denominator. the points where our function is not going to be continuous. These are points plus and minus 2. So combining these three statements, then function f of x is going to be continuous on the following intervals from 0 to 2, union from 2 to plus infinity. All right, next theorem is the squeezing theorem. Let's assume that we have function f, g, and h, and they satisfy the following condition: g of x is less or equal than f of x, and f of x is less or equal than h of x. For all x in some open interval containing the number c, with the possible exception that the inequalities need not to hold at c. We mean by that statement that they can be equal to each other at point c. If g and h has the same limit as x approaches c, say limit as x is approaching to point c of g of x is equal to limit as x is approaching to point c of h of x and is equal to some big L, then f also has this limit as x is approaching to c. A simple geometrical representation of that theorem is given here. So we have functions h of x, so h of x is greater or equal than blue function here, which is f of x, and f of x is greater or equal than function g of x, this function below in green, with the possible exceptions that inequality not necessarily should hold at point c, so they can be equal to each other at point c. And if limit of that purple function and green function approaches the same value, a big L at point C, then you can see that these two functions, they are going to squeeze in this blue function, and limit of blue function at point C is also going to be equal to big L. That is a really useful theorem. We can use it to prove the following limits. So limit as x is approaching to 0 of sine of x over x is equal to 1, and limit as x is approaching to 0 of 1 minus cosine of x over x is equal to 0. All right, so first of all, let's take a look at the following visual we have here. We have a unit circle, and we have an angle x. For starters, let's assume that x is an interval from 0 to pi over 2. Then a similar proof can be extended for x in interval from minus pi over 2 to 0. Let's take a look at the following three areas. Area of a triangle, where we have a first triangle is a triangle with one of its bases equal to 1, and hypotenuse extending from our angle x here. Then height of that triangle is going to be equal to tangent of x. Second, we have an area of a sector. Area of a sector is equal to x over 2. So the reasoning is following. This angle here is x, and it makes up x over 2 pi, fraction of our whole circle. And the area of a whole circle is equal to pi r squared. Radius here is equal to 1. So this is x is equal to 2. And obviously, an area of that triangle is going to be equal to tangent of x multiplied by 1 divided by 2. Next, we have the following triangle. An area of this triangle is equal to 1 multiplied by sine of x. Sine of x is given as height here, since we have unit circle here and hypotenuse here. Not hypotenuse, one of its bases is equal to 1. So hypotenuse of that small black triangle is equal to 1. And this angle here is equal to x, meaning that this height here is equal to sine of x. So area of that triangle is equal to sine of x over 2. And let's take a look now at these three areas we presented. We see that This sector is inside of this big triangle, and this right triangle is inside of this sector here, meaning that an area of that big triangle is greater or equal than area of sector and greater or equal than area of a small triangle. Now let's try to bring that inequality to the following form, such that we'll have this function here in the middle, and then we are going to use squeezing theorem. To do so, we have to divide all three inequalities by sine of x over 2. Let's recall that we are now working with the case when x is in interval from 0 to pi over 2, meaning that sine of x is going to be positive. So the sign of inequalities, they're not going to change. All right, so then we are going to end up with, so here we have sine of x over cosine of x over 2 cosine of x. So we'll end up with 1 over cosine of x greater or equal than, so we have x over sine of x, and greater and equal than 1. All right, now flipping our inequalities, we'll end up with sine of x over x less or equal than 1 and greater or equal than cosine of x. Okay, now using squeezing theorem, we see that sine of x over x is squeezed between functions cosine of x and 1, taking limit as x is approaching to 0 of cosine of x. This is equal to 1, and limit as x is approaching to 0 of 1 is equal to 1, meaning that by squeezing theorem, limit as x is approaching to 0 of sine of x over x is equal to 1. All right, now proof for the case when x is in interval from minus pi over 2 to 0 is similar. Try plugging in minus x instead of x in that inequality here, and you will end up with the same result. Now let's show part B. So we are going to start off by multiplying both numerator and denominator by the conjugate of numerator. We'll end up with 1 minus cosine squared of x, so over x, 1 plus cosine of x. Now in numerator, we will have sine squared of x over x, 1 plus cosine of x. Let's split this up as a limit as x is approaching to 0 of sine of x over x multiplied by limit sine of x over 1 plus cosine of x as x is approaching to 0. So we can split this up in the following manner, since we know that this is equal to 1, and that limit is also finite, exists. It is equal to 0 over 2, which is 0. So the answer is then 0. Okay. Now let's take a look at the following two limits. First limit here, when x is approaching to 0, either from left or right hand side, then 1 over x will go to minus infinity or to plus infinity, meaning that sine of 1 over x is going to fluctuate between minus 1 and 1. So that limit here doesn't exist. And we can see that from the graph of sine of 1 over x here. We see that the values of sine of 1 over x, they fluctuate between minus 1 and 1 and as we are approaching to 0. Now, second, we have a limit x multiplied by sine of 1 over x. Now let's take a look at the value of x multiplied by sine of 1 over x. sine of 1 over x is going to fluctuate between values of -1 and 1, meaning that this product here lies in interval from minus absolute value of x to plus absolute value of x. So basically here we are just multiplying x by some scaling factor that is in interval from -1 to 1, meaning that at most values of x is going to lie at most the values of x is going to be equal to absolute value of x, and at worst x is going to be equal to negative value of absolute value of x. Here now we can use squeezing theorem, and since limits as x approach to 0 of minus absolute value of x is equal to 0, and limit as x is approaching to 0 of absolute value of x is also equal to 0. Those two functions are going to squeeze in our function here, and limit as x is approaching to 0 of x multiplied by sine of 1 over x is also going to be equal to 0. And we can confirm that by looking at the graph of x multiplied by sine of 1 over x. So here we can see that these two lines, x bar, absolute value of x and minus absolute value of x, they squeeze in our function of x multiplied by sine of 1 over x. At that point 0, limit of that is equal to 0. All right, guys, now that concludes our lecture on section 1.6 on continuity of trigonometric, exponential, and inverse functions. Thanks for watching.